All right, in today's lab, what we're going to be doing is determining an experimental value for that Boltzmann constant. That constant relates temperature and energy that shows up in a bunch of different places in thermodynamics. We're going to figure out what that value is. We're going to do that with an experiment. We're going to use the ideal gas law, which relates the pressure, volume, number of particles, Boltzmann constant, and temperature. In order for us to be able to do that, we need to know what all of those other 4 variables are so that we can figure out what that Boltzmann constant is. Pressure and volume are pretty easy to determine. With volume, we can just read a value off of a syringe. With pressure, we'll be using a Vernier pressure sensor, which measures the pressure in kilopascal. Temperature is pretty easy too. Thermometer is good enough. But number of particles, that's tricky. We could get a known volume of gas and then use the ideal gas law to figure out the number of moles, but that would require already knowing what Boltzmann constant is. I have a different idea. We're going to use this product. It's called Bloxygen. It's really just pure argon. The website says it's made of ultra pure argon, and the MSDS lists it as argon. Argon is a gas. It's a noble gas. It has a known molar mass. So if I can figure out the number of grams of argon, then we'll know the number of moles of argon. Number of moles of argon and Avogadro's number gives us the number of particles of argon. That's our ticket in. But how do we measure the number of grams of gas? Let's take a closer look. I have here an analytical balance. It measures masses out to 1/10 of a milligram, which is pretty small. I'm going to be using it to determine the mass of the argon gas added to this syringe. That way I'll be able to calculate, using the molar mass of argon, the number of moles, and using the Avogadro's number, the number of particles, or molecules, or atoms in this case, since it's monatomic. Now, I can't just measure the mass of the argon that's directly added to this syringe, because as I add argon in here, it's going to expand, which means that its volume is going to increase, which means that the buoyant force that this syringe feels will also increase. So either I take the mass measurements in a vacuum to negate the buoyant force, or I have to think of another way. So what we'll do is we'll take the mass of the can, since it doesn't change in volume, it's metal. So we'll have to carefully measure the mass of this can, and since it sticks up over the top and we want it sealed to prevent air currents from disturbing our value, because it's down to 1/10 of a milligram, we'll need to put a cover over the top just to prevent any air currents from disturbing the reading. Once we've done that, we'll record that initial mass and then use the provided straw to actually fill up our syringe, seal it off with a valve, and then measure the mass of the can again. In doing so, we'll be able to take the difference of those two numbers, and that should give us a very accurate value for the mass of the argon added to the syringe. With a thermometer, and by reading the values on the side of this syringe for milliliters, and using the pressure sensor attached to the top of this for measuring the pressure, we should be able to produce an experiment that allows us to determine the value of Boltzmann constant. Let's give it a go. You ready? Okay, so we're going to begin our data collection by connecting the pressure sensor to the argon gas sample. And then we will begin compressing the gas slowly to make sure it is an isothermal compression. All right, and we'll stop right there.